Hey guys, Professor Doney here. Again, we're in the middle of projectile motion, two-dimensional motion. And we do a problem here where we drive right off a cliff. James Bond goes off the cliff. The guy from the transporter, anybody, drives a bike, car, four-wheeler, whatever they want to do, off this ledge. It's 10 meters high. That's about the third story, third floor, a little higher than that, at 20 meters per second, which is around 44 miles an hour, just to give you an idea. And basically what we want to know is find out how far away do they land. Now while we're there, we're going to find out how much time they are in the air also, because that becomes very important in us calculating how far away will they land. So that's our problem. You're going to drive off a cliff for whatever reason and land below. We want to know where to pick up the car or pick up the pieces or put the swimming pool you land in, however you're looking at the problem. Alright, again, two-dimensional problem. Since we're driving off the cliff and it says nothing about going up or down off a ramp, we're going to take that initial velocity as being in the x direction, 20 meters per second horizontally. That means vertically it's going at 0 meters per second, meaning it's not being thrown up or thrown down because it goes off a ramp or goes down a ramp. Okay? Alright, so what do? We know how fast it's going away. We know how high up. High up is going to be the delta y. That tells us 100 meters. Okay? It basically tells us the height we're going to fall from. Now, as we look at projectile motion problems under the influence of gravity, obviously gravity is always down. This object is falling downward. The reason it falls is because of gravity. Now, we should have seen already in the lecture that this time to fall out here along this path is equal to the time it would take to fall straight down. Even though visually this looks like they're in the air longer, they're actually falling the exact same distance, 100 or 10 meters. We just see it fall further out and our brain tells us, hey, we're in the air longer. That's why when they dunk from the top of the key, if you watch hoops, it looks like they really have some hang time versus just jumping straight up and down underneath the basket. So what we need to do is find out this time, and when we know this time, we can go and calculate the distance. So basically what we're going to do is start out by doing a drop problem, and we're going to drop it from 10 meters. We want to know how long it takes the object to fall 10 meters. So we're going to use delta y v0t half gt squared. I'm going to pick positives down. Why? Because everything's going that way. I know it's 10 meters. I know initially it's 0 because it's not going up or down. Half 9.8 t squared. So we come out to be t is the square root of twice 10 over 9.8. And that's the square root of 20 over, I'll do this quick, divided by 9.8, about 1.42 seconds. Alright. That should be a 1 there. Okay? That's how long it's in the air, whether it goes out on this path or whether it falls this distance. Now, what are we going to use with that number? Well, we're going to go back to horizontal. We want to know how far away it lands. We go back in the horizontal direction. This is the only real equation we have because the acceleration in the x direction is 0. So all our equations are 3 constant acceleration equations reduced to that. So initially, how fast are we going in the x direction? The problem tells us initially we're going 20 meters per second. How long we are in the air? For 1.42. If I take 20 times 1.42, I'll get a 284, and I think that becomes 28.4 meters. It tells us how far they land. So, real quick problem on that. Hope that helps you out. Here comes my son.